So of course, there's lots of equilibria that are going on right here. And so if you throw in a metal ion, and we'll just call that metal ion Mn plus, N plus being the variable oxidation state of this metal. If we throw that into solution, and that metal ion could be in equilibrium with any one of these various speciated EDTA species. That makes for a really complicated equilibrium system, and we actually don't need to know all of the equilibria to get the information that we actually need about the system. And the information that we actually need about the system often is just the concentration of the metal ion in solution, or the unbound concentration, in which case, by convention, typically we talk about only one formation constant for EDTA, and so we write that out as manganese, Mn plus Y4 minus, so we just write the complexation in terms of Y4 minus, and that goes on to form the complex form where the Y4 minus is complexed the original metal, so that would be N minus 4, and this equilibrium constant we write as Kf, or the formation constant for that particular complex. And as I said, the convention for EDTA complexation is to use the Y4 minus as the species that's complexing Mn plus. I need to be really clear here that by writing this way, and your textbook writes it this way because this is actually just the convention, that does not in any way imply that all of these other species that are present here will not have by themselves some other equilibrium with that metal ion. They almost certainly will. It's just that it's not necessary for us to write out all of those equilibria to deduce the information we need. Instead, we're just going to write out things in terms of the Y4 minus form of the EDTA species. Or in other words, the Y4 minus here is essentially going to serve as a proxy for the entire system. So because the Y4 minus has literally 4 minus charges on it, and these dentate ligands, this tetradentate ligands that can sort of fully encapsulate metal ions, as I mentioned or alluded to before, that Kf, that binding constant or formation constant for the complex, is usually really large, meaning there's a great affinity for metal ions by the Y4 minus complex. So what I tossed in here are Kf or log Kf values for Y4 minus. They say for metal EDTA complexes, but because the convention for metal EDTA complexation is Y4 minus, that's what it really means, is the Kf for this reaction. And you can see that for several of these metals, especially as the charge increases and the size decreases, the Kf, the log Kf value is quite large. So for instance, like vanadium here, the vanadium ion has a log Kf value of 25.9, which means Kf is going to be equal to 10 to the 25.9. That's an enormous, enormous, enormous number, which tells you that the propensity for this complexation to occur, meaning if you throw EDTA into a solution with vanadium 3+, you can rest assured that every single bit of vanadium 3+, within reason, is going to be complexed. That's even more true if you have something like thallium, right? That's going to be 10 to the 35th. But even things like lithium, we're talking about fairly small ions that are positively one charged, are going to have a Kf value of nearly 1,000 or 10 to the third. Things like potassium and sodium, those are larger positive ones, and remember, larger ions are going to complex less strongly, simply from the notion of, if you've got lithium, sodium, and potassium, they're the same charge but just distributed over different volumes. And so the charge density on lithium is going to be quite a bit higher than the charge density on sodium, which is going to be higher than the charge density on potassium. So instead of thinking just simply about charge, we're thinking about charge divided by surface area of the ion, in which case we see this trend where maybe potassium is not binding, but typically potassium is not a good methodology for EDTA. But almost all of these other metals, the values are quite high, significantly high enough that we can assume that 100% of the metal is complexed when EDTA is added. I should also mention that simply based on the shape of EDTA, those 4 ligands will wrap around all metal ions, but they won't include more than one, meaning the stoichiometry between the metal ion and Y4 minus is always going to be 1-to-1. And that makes also for an especially useful analytical tool, because it's not complex stoichiometry that changes depending on the metal ion. It's always going to be 1-to-1 simply based on the sterics of the ligand. So the equilibrium expression then for this Y4 minus complexation with an arbitrary metal ion is just going to be the complex concentration divided by the metal ion concentration multiplied by Y4 minus. That's Kf. So the utility in this expression is it allows us to compute what the metal ion concentration is at whatever this equilibrium is in a particular system, but it requires us to know the Y4 minus concentration. In order to know the Y4 minus concentration, the easiest way to get to that would just to simply use the alpha diagram, because the alpha diagram would allow us to compute exactly what fraction of the EDTA is in that form at the given pH. So this table comes out of your textbook and allows you to actually know what the fraction of Y4 minus is as a function of pH without having to have or extract the values directly from the alpha diagram itself. And so it tracks as you'd expect, right? Y4 minus becomes much more abundant as the pH increases. And so it's not until you get to pH 9 and 10 that you have a reasonable amount of this in solution. Okay, so where are we going with this? Well, this is our operative expression. This is the thing that we're going to need, but we need to adjust this expression for the Y4 minus not being the dominant species in solution. Or in other words, we don't know what that is, but we do know what the fraction of it is. And so we're going to adjust this equation slightly before we use it. So start by remembering what the definition of that alpha Y4 minus is, a fraction of Y4 minus. It's simply just the concentration of Y4 minus over the total formal concentration of EDTA in solution, or the sum of all of the different species at a given pH. So we can just rearrange that solve for Y4 minus, and then the utility in that is we can just take this Y4 minus and substitute it in directly, sort of as I had alluded to before. So now Kf is in terms of the alpha, which we can just grab from a table or from an alpha diagram, which is essentially a constant or fixed as a function of whatever pH. And it's in terms of the total EDTA concentration, which we know if we're making up a solution. We often can make up a solution and it'll be 0.1 molar EDTA, but we won't know exactly the concentrations of all the species. We'll just know that we threw a total of 0.1 moles of EDTA per liter of solution into that system. And then if we know the pH of that system, then we know the alpha, and if we know both of those, then this becomes a solvable expression. So if I substitute that alpha portion into the original equilibrium expression, I get this expression here. And then what we can do is just take this alpha portion and just divide it into Kf. So we essentially adjust our constant in the equilibrium expression for what fraction of Y4 minus is actually present in the solution at that given pH. So we're modifying our Kf, and we call this thing a conditional Kf. The conditional Kf goes as, we just write that as K prime F, simply because it's been modified. It's similar to when we modified equilibrium constants before by activity, in our Chapter 8 section, it's really similar, where we're modifying the constant because those two things are constant. We're just collecting the constants in a single term. All right, so you rearrange that or divide that alpha in, so you get an expression that looks like this. And so this is our operative expression. We started with this, our kf, and we modified it to this with our conditional kf simply by incorporating a little bit about what we know about the system, and that's that the concentration of Y4 minus is conditionally dependent on the pH, and we can correct for that by using its fraction or the alpha diagram of EDTA at that given pH.